In this lecture, I will solve examples based on series diode configuration. In the first example, we need to determine V0 and ID. V0 is the potential at this point, and when you complete this circuit, you will find V0 is the voltage across this resistance. ID is the current flowing through silicon diode, and minus 5 volt is the potential at this point. We can also redraw this circuit like this. We are using silicon diode, so the barrier potential is equal to 0.7 volts. 2.2 kilo ohm is the value of resistance. V0 is the voltage across this resistance, and we have to find out polarity of V0. V0 is positive. V0 is positive in this circuit, so I will connect positive terminal of V0 to this node, and a negative terminal of V0 to this node. Positive negative V0. This is 2.2 kilo ohms. In the same way, we need to determine polarity of minus 5 volts. This is negative, so I will connect negative terminal to the N side of the diode. This is silicon diode. ID is the current flowing through the diode, and positive terminal like this. This is how this circuit will look when you include the potential differences instead of potential at point. Minus plus 5 volt is the potential difference. V0 is also the potential difference, but in this circuit V0 is potential at point, minus 5 volt is also potential at point. So there is only one difference between these two circuits. In this circuit, potential at points are given, and in this circuit, potential difference is given. In exam, we are not going to make this circuit. I have explained this circuit only to clear your basics. We are going to obtain all the values using this circuit only. So the first thing that I will explain is how to deal with potential at points. How to deal with potential at points. And for this, I will take one example, a very simple example in which potential at points are given. This is point A. VA is the potential at this point. There is another point B. VB is potential at this point. And here we have potential difference of 5 volts with this polarity, 5 volts. Then we have potential difference of 6 volts. After this, there is potential difference of 8 volts, and final potential difference is equal to 15 volts. So these are the 4 potential differences given in this circuit, and we need to calculate VA minus VB. VA minus VB is nothing but potential difference between point A and point B. So let's see how we can solve this problem. We will start from VA and move towards VB with final value equal to VB. VA minus 5 volts because of this polarity, plus minus. Then we have plus 6 volts because we have minus and plus as the polarity of 6 volt. After this, we have 8 volts, and final potential difference is minus 15 volts equal to VB. This is how you have to deal with potential given at points, and now we can easily calculate value of VA minus VB. When you solve this, you have VA minus 6 volts equal to VB, or we can write VA minus VB equal to 6 volts. This is the answer. Sometimes in the problem you need to calculate potential at point. VA is potential at point, VB is potential at point, and all these 4 voltages are potential difference. And sometimes we need to calculate potential at point. For example, if VB is equal to 4 volts and we have to calculate VA for this situation, then let's see what we can do. We can easily calculate VA. VA is equal to 6 volt plus VB. VB is 4 volts, so VA is equal to 10 volts. This is the answer. I will use this approach to solve this problem. In this problem, we need to calculate V0 and ID, and the first thing is to find out state of diode, whether this silicon diode is on or off. and you can see the direction of current is matching with the direction of arrow. So the silicon diode is on, and I will replace this silicon diode with its equivalent circuit. Equivalent circuit is nothing but a potential difference of 0.7 volts. This is the polarity. V naught is the voltage across this resistance, 2.2 kilo ohms. The direction of current ID is like this. Potential at this point is minus 5 volts. I will start from minus 5 volts. I will start from minus 5 volts and move towards V naught. So we have minus 5 volts plus 0.7 volts equal to V naught. So V naught is simply equal to minus 4.3 volts. This is the answer. You can see how simple it is to calculate the values using the potential at points. Now we will find out value of ID, the current flowing through the diode. I will start from 0 potential. This is ground, and potential of ground is equal to 0 volts. We will start from this and move towards V naught. 0 volt minus 2.2 ID. Potential drop across this resistance is equal to 2.2 ID equal to V naught. And we have already calculated V naught. It is equal to minus 4.3 volts. So we have 2.2 ID equal to minus 4.3 volts, or ID is simply equal to 4.3 volts divided by 2.2 kilo ohms, and this is equal to 1.955 milliamps. This is the answer. So the two values that we had to calculate in this problem was V naught and ID, and we have easily calculated them using the potential at points. In the second problem, there are two diodes. First diode is silicon diode and second diode is germanium diode. Plus 20 volt is the potential at this point. So direction of current will be like this. Let's say ID is the current. Direction of current is similar to the direction of arrow. So both the diodes are forward biased, and I will replace them with their equivalent models. In case of silicon, the barrier potential is equal to 0.7 volts. So we have 0.7 volts here. And in case of germanium, barrier potential is equal to 0.3 volts. 2 kilo ohm is the value of resistance. 2 kilo ohms. Potential at this point is equal to V naught. Potential at this point is equal to plus 20 volts. There is another resistance connected like this, having the same value, 2 kilo ohms, and I will use the same approach to calculate the value of V naught. First I will calculate ID, the current flowing in this circuit. I will start from 20 volts and move towards 0 volt. 20 volts minus 0.7 volts, 0.7 volts minus 0.3 volts. Voltage drop across this resistance is equal to 2 ID. Voltage drop across this resistance is also equal to 2 ID. When you solve this, you will find ID is equal to 4.75 milliamps. Now we will calculate V naught. Start from V naught and move towards the ground. So we have V naught minus 2 ID equal to 0 volts. When you solve this, you have V naught equal to 9.5 volts. This is the answer. Now I will solve the third problem. In this problem, there is silicon diode. Plus 20 volt is the potential at this point, minus 10 volt is the potential at this point, and it is clear that the direction of current is like this, and the direction of current is matching to the direction of this arrow. So the silicon diode is on. I will redraw this circuit with equivalent model of silicon diode. We have potential difference of 0.7 volts in place of silicon diode. Minus 10 volt is the potential at this point, plus 20 volt is the potential at this point. 6.8 kilo ohm is the value of resistance. This is V naught. I will first calculate the current ID. I will start from 20 volts and move towards minus 10 volts. 20 volts minus 6.8 ID minus 0.7 volts equal to minus 10 volts. So ID is equal to 20 volts plus 10 volts minus 0.7 volts divided by 6.8 kilo ohms. So ID is simply equal to 4.30 milliamps. This is the answer. Now I will calculate the value of V0. I will start from 20 volts and move towards V0. 20 volts minus 6.8 ID equal to V0. So V0 is simply 20 volts minus 6.8 kilo ohms multiplied by 4.30 milliamps. When you solve this, you will find V0 is equal to minus 9.3 volts. This is the answer. So this is all for this lecture. If you have any doubt, you may ask in the comment section. In the next lecture, we will start series parallel configurations of PN junction diode. So see you in the next presentation.